Okay, greetings, aspiring scientists. Today we're doing the dreaded experimental uncertainties topic. And let's be honest, this sucks. This is quite a dry and boring and seemingly not that important and very easy to make mistakes, very difficult to do it properly. So all those things combined together makes this kind of one of the most hated things, I think, in the science curriculum. And yet, I have great respect for it. I have learned to really appreciate it, and so I'm going to teach it with the same clarity and passion and respect that I would for any other topic, or at least I will try. So, let's get started. Going to my slides here. Tools, experimental uncertainty. So first we need some vocabulary. What is accuracy and what is precision? We might use these terms interchangeably in everyday speech, but in science they have specific definitions that we need to use and not mix up. So accuracy, this is the closeness of the agreement between the result of the measurement and a true value of the measurand. By the way, I get these definitions from the IUPAC Gold Book. IUPAC is generally like the organization that most schools and scientific communities use for reference, so that's why we will use it. Anyway, so closeness of the agreement between the result of a measurement, that's something that you get from your instrument or from your eyes making a observation, and the true value of the measurand. The measurand is just the quality or the property of the sample that you're trying to measure. So these things are slightly different, right? There's the true value, and then there's what you measure, and they'll almost never be exactly the same. We can say basically they will never be exactly the same. But the closer you are, the higher your accuracy is. The closer you are to the truth. The farther away, the lower the accuracy is. The term precision should not be used for accuracy, and accuracy is a qualitative concept. So we don't really have any boundaries per se set by this organization for what is considered good accuracy or not. That would be quantitative. But we can just say that the closer we are to the truth, the higher the accuracy. The farther away we are, the lower the accuracy. In that sense, it's qualitative. Alright, what about precision then? The closeness of agreement between independent test results obtained by applying the experimental procedure under stipulated conditions. The smaller the random part of the experimental errors which affects the results, the more precise the procedure. A measure of precision or imprecision is the standard deviation. You might have heard that before. Alright, so we have some method that we're going to apply to our sample or try to take a measurement using some procedure with our instrument. And we're going to repeat it over and over and over. You might expect to get the same results every time, but in the real world, you won't. There's going to be some what's called random error, random variance. And basically, the closer your results are to each other each time or to some average value, the higher your precision is. The bigger that variance, or the more standard deviations, or the greater the standard deviation is, the higher the random error is, the lower your precision is. So the analogy that we usually use for this is like throwing darts at a dartboard where the bullseye represents a direct hit on the truth. And since we have two properties here, we have four possible combinations. We could have low precision and low accuracy here on the left, top left, where my arrows are all over the place. They're widely spread out, and that's low precision. And if you were to take the average of these, it would be somewhere on the right, quite far away from the truth, far from the bullseye. Then on the right, top right, we could have high precision, low accuracy. So this would be, our measurements are consistent. We're quite near the same value every time we throw a dart or we take a measurement. But it is far away from the truth, right? Our measurement is far from the measurand. We're not close to hitting the truth, which is low accuracy. Then on the bottom left, we could have low precision, high accuracy. So each time we throw the dart here, these arrows represent the darts where they land, and the average of these four is probably actually on the bullseye. It's quite near the truth. But would you trust me to throw one dart and get an accurate result? Probably not, because I have low precision here. Every time I throw it, these darts are far apart. I need to take the average to actually get near the center, or near the bullseye, near the truth. Okay, and then in the bottom right, we have what we all strive for: high precision and high accuracy. I get near the truth every time, and every time my results are close to each other, which is close to the truth. So we strive for high precision and high accuracy, but oftentimes you'll have more of one and less of the other, and it's up to you to analyze what you can do to fix your errors. So, systematic errors versus random errors. This is also related. So, systematic errors are related to accuracy. Random errors are related to precision. What are the definitions then? Systematic errors are caused by a fault in an experimental method that causes measured results to be displayed either consistently above or consistently below the true values. So every time we take our measurement, we're going to have a greater chance of being either too high or too low by some factor. That's a systematic error. We have to go into our experimental setup and try to fix something, either our method or our instrument. Random errors then. Random errors are caused by random fluctuations in a sample or its environment that causes variance in measured values between trials. This variance has no preference in direction. Okay, so these are kind of my definitions of these, by the way. I didn't directly take these from a source, but this is just what's been in my mind after reading several textbooks and online descriptions of this. All right. So these are quite different, and there's different ways to fix these. We'll consider in a moment. But it's important that random error is not directed in any particular direction, not too high or not too low above the truth. It might seem like that at first, but as you take more and more measurements, you'll see that there is no preference for being too high or too low with random errors. Let's consider a systematic error example. This is a caliper. This is used to measure distances or lengths very accurately. But, okay, many instruments, even those that have been rigorously calibrated, will eventually experience drift due to constant usage or even lack of use over time. So in this image, this caliper reads 0.04. Can't quite see the units there, but it's probably centimeters. Even when the jaws are closed. So this instrument has like these two jaws. These are what measure the actual length. But here they're actually already closed. It should read 0. And yet we have a reading here 0.04. So this is going to be a systematic error. The caliper reads 0.04 even when the jaws are closed. The solutions are you can subtract 0.04 from all your measurements that are made in the future. But that's annoying, right? You might rather just try to recalibrate this instrument. You can recalibrate it and fix a 0 error by hitting the 0 button. You can see right in the middle underneath the screen there. There is a button that says 0, so you can hit that and redefine where 0 is. And then the instrument will basically do that subtraction of 0.04 for you and just display the correct numbers that you can write down. So a lot of instruments have calibration in this way. Yeah. So that's an example of a systematic error. It's not the only type though. There are basically unlimited. If you want to suggest anything to me in the comments and consider whether it's a systematic error or not, you can do that. And I'll let you know my opinion too. Anyway, I got this image from some website, moglix.com, Vernier calipers, if you're interested. Random error. So let's consider a statistical frequency plot. This will show us basically results on the x-axis and then the frequency of those results on the y-axis. So if we had no random error, we might expect this kind of thin, what's called a normal distribution, a bell curve that has a particular average right in the center. But as we introduce random error, what we're introducing, or when we increase random error, we're increasing the variance, the possible range of outcomes that we tend to often get. And so we get this curve on the outside. It's fatter, and yet if you were to take the average of the frequencies in this curve, it would be exactly the same as with no random error. Okay, it's just we have greater possible variance, we have greater possible amounts of outcomes, common outcomes anyway. So this is what I think random error is, and it's a good representation of it. This is from circa.carleton.edu website that I found, but I just really like the presentation of this graph, so hopefully they don't mind me borrowing it. Practice question then. A student performs a measurement with a standard lab instrument. She then repeats the exact same process 9 more times. The results come out slightly different each time, but she takes an average of all the measurements to carry forward to future calculations. Which aspects of systematic and random error has she influenced? In what way? All right, think about that for a minute. You can pause the video, maybe write down what you would say. But I'll give you my opinion here. So what aspect of systematic error has she influenced? I would say basically nothing. She had a method. She didn't change anything about it. She repeated it 9 times. If you repeat the same thing over and over, you're not going to be fixing or changing any systematic errors. So no influence there. But random errors, we've seen that the average of a system with random errors and the average of a system without it are basically the same. You just need to have a better average. And the way that you get a better average is by taking more measurements and averaging those measurements. So she'll have greatly reduced random error by taking 9 trials or 9 measurements using the same method here, I would say. So reduced random error. Another question here. A student performs a measurement with a graduated cylinder. She takes a measurement but realizes that she's looking at the meniscus. If you watched my first video on science and math communication, you'll know the meniscus is that little curve that liquids make when they're in a container. And the bottom of the meniscus is where you need to measure volume amounts from. But she realizes that she's looking at the meniscus from above instead of bringing it to eye level. So she deletes her previous result, her one measurement, and repeats that measurement while kneeling to keep the meniscus at eye level. Again, which aspects of systematic and random error has she influenced and in what way? You can think about that for a minute. Now, I'll give you my opinion. So she has fixed a systematic error here. She was looking at the meniscus from above. It's something called parallax error. You need to look at it on the same level, right? Eye to meniscus on the same plane. So she was probably getting results that were, I guess, too low previously. And it was consistently too low because she was consistently looking at it from above. And by fixing that error, kneeling down, she's greatly reduced her systematic error. From this source of systematic error, there might be others, we don't really know. What about random error? She hasn't influenced it at all. She's taken one measurement, deleted it, and then retaken it. So basically that's 1 or 2 data points, depending on how you think about it. Not really good enough to get a reasonable average and to overcome any random error that's in this environment. Okay, so then what the heck is experimental uncertainty? Experimental uncertainty is important to describe how confident we are with a measured number by providing an exact or an expected range. So this is very much like my definition of significant figures was. Those are also to describe how confident we are in a measurement. But the uncertainty will provide us with a range around some central value. So we're going to have a minus range and a plus range that will provide us with a total range that we are going to say we are confident the results are inside of that range. So experimental uncertainties must have the same number of decimal places as your measurement. At least this is true for a particular type of uncertainty called absolute uncertainty. And that's what we're going to start with. So this is what I'll say is a rule for now. If you're in scientific notation, your uncertainty must have the same power of 10 as your measurement. Again, this is true for absolute uncertainty. So if our measurement is times 10 to the power of 4, our uncertainty should also be times 10 to the power of 4. And one way to think about why that is, or to think about the reasoning for that, is if you watch my scientific notation video and significant figures video, you'll know that when we subtract or add, we want things to be in the same power of 10 for it to make sense and to be convenient. Basically the same thing here, because we're going to have plus or minus some value to indicate our range. So that plus or minus number needs to be in the same power of 10 as our measurement. Okay. So uncertainty will be written as a number, which is our measurement or calculated value, plus or minus. That's how you read this plus dash minus that I've written at the bottom of this slide. Plus or minus an uncertainty value. So we could have something like 10 meters plus or minus 1 meter. That would indicate that I'm confident the length of whatever I'm measuring is between 9 and 11. That's 10 plus or minus 1. Okay, so how do we measure a digital measurement with its uncertainty? So here we have an analytical balance with a block on it reading 100.00 grams. So the generally accepted absolute uncertainty for digital instruments is the smallest possible measurement that the instrument can indicate. So it's a little difficult to see here, but this is 100.00 grams that's on the display. So you know that the smallest amount that this balance can measure is 0.01 grams. Anything smaller than that and it will register like 0 or non-detection. So when you write this measurement with uncertainty, you will write 100.00 plus or minus 0.01 grams with the units written at the end there, G for gram. Okay, so digital instruments are easier. That's just the rule. You take the smallest possible measurement that it can make, treat that as a plus or minus uncertainty. This is an example of an absolute uncertainty. What about analog measurements? So here I've got a pencil. This image was generated by ChatGPT, but I think it's good for us to use. So there's a rule for analog measurements and uncertainties. You can get an extra significant figure beyond what the analog instrument indicates. If you watched my video on science, math, and communication earlier, I introduced that rule, but I said it's related to experimental uncertainties. So we'll discuss that here. Each time you take a number reading, an uncertainty must also be applied. So you might think we're just measuring the length here and that's one reading, but you actually need to make two decisions and two measurements with your eyes and with your brain here. The first is, where does this pencil start? And the second is, where does it end? So the generally accepted absolute uncertainty for analog instruments is half of the smallest scale division. So looking at this ruler here, the smallest scale division is 1 millimeter. The units are not actually labeled on here, but come on, we can trust that the numbers 1, 2, 3, 4, 5, and so on indicate centimeters. There's 10 lines in between them, so one small line indicates 1 millimeter. Then we can take half of that as our uncertainty. So half a millimeter is the uncertainty. We're going to do plus or minus half a millimeter. So what does that look like? Applying the rule to this measurement, the left side of this pencil is around 1.0 centimeters. That might be what you think is the measurement for the left side here, but remember you can get an extra significant figure beyond what this instrument shows, so you can write instead 1.00 plus or minus half a millimeter. So a millimeter is 0.1 centimeters, half a millimeter is 0.05 centimeters. Think about that carefully for a second, but it is true. So your measurement for the position of the left side of this pencil is 1.00 plus or minus 0.05 centimeters. All right, and I mentioned before the decimal places here have to match. So 0.05, the position of that 5 matches the digit farthest to the right on the original measurement 1.00. Okay, so you could not write something like 0.005. That would be like too many decimal places in your uncertainty value. And you could not write something like 0.5. That would be too few. You would have to write 0.50 to have the same number of decimal places here. Anyway, what about the right side in blue here? So the right side is at around 16.5 centimeters. This needs to be taken as 16.50. Put in your extra significant figure, plus or minus, again, half a millimeter, 0.05 centimeters. So we still have not indicated the length of this pencil. We're going to do that later on in this video. I want to remind you there's a relationship between fractional or proportional fractions, decimal numbers, and percentages. These can all represent the same thing, just in different ways. So when you have two things with the same units into a fraction like this, you can also divide those numbers in your calculator and get a decimal number. You can multiply that by 100% to get a percentage, and you can go in reverse of these as well, but they all represent the same proportion. So why do I talk about that? It's because we need to understand something called relative uncertainty. So relative uncertainty, look at the right side here first. This is the absolute uncertainty divided by the measurement. So before, when I said something was like 10 meters plus or minus 1 meter, you would take that plus or minus 1 meter, put it on the top of a fraction, and take the 10 meter measurement and put it on the bottom, and you'll get 0.1. That's an expression of relative uncertainty, and we're going to write this as delta A over A. And relative uncertainty and fractional uncertainty, I think, can be considered the same thing. You'll see both of them used. So a measurement with absolute uncertainty, that's what we have been discussing up to this point, can be expressed as A plus or minus delta A. So for example, 10 meters plus or minus 1 meter. A measurement with relative uncertainty can be expressed as A plus or minus delta A over A. So just as I discussed, we had plus or minus 1 meter on 10 meters, that was 0.1. So you can write 10 meters plus or minus 0.1. Now when you make that fraction, the units will disappear because you've got meters on the top, meters on the bottom, they cancel out to 1. So the fractional or relative uncertainty part of that, delta A over A, has no units anymore. And you'll also see percentage uncertainty sometimes. This is just relative uncertainty times 100%, just like I showed on the previous slide. So with my example of 0.1 relative uncertainty, that ends up being 10%, plus or minus 10%. That's if I have plus or minus 1 meter on a measurement of 10 meters. So you need to know all of these, both how to read them and understand them, and how to use them and express them. All right, I want to introduce you another method to generate uncertainties. So previously we were looking at instruments, but now we're going to look at somebody who's doing multiple trials. So a student measures the temperature of a room 5 times from different locations around the room. They measure 298.1 Kelvin, 298.5 Kelvin, 297.9 Kelvin, 298.4 Kelvin, and 298.9 Kelvin. But they're just trying to measure the average temperature of this room, one temperature to represent the whole room. So the measurement for the average temperature of the room that the student should take is the average of these, all added together divided by 5, because there are 5 measurements. So that's basic statistics. I'm going to assume that you know that. So this ends up being 298.4 Kelvin, rounded up a little bit from 298.36, just so I can keep my 4 significant figures. Now, there's something called the range of these measurements. The range is the highest minus the lowest. So the highest was 298.9, the lowest was 297.9. That means the range of the measurements that this student collected is 1.0 Kelvin. Now your absolute uncertainty in Kelvin can be taken as half of this range. And that should make some sense to you, because when I introduce to you what uncertainty is, it's some range around an average value. So if you take half of that range, that's your plus or minus number, right? So the result of this student's collections and trials is therefore that the average temperature of this room is 298.4 plus or minus 0.5 Kelvin. So this output looks essentially exactly like the outputs for the previous experiments we saw using a digital or analog instrument. It's just it came through a different method of somebody doing multiple trials and taking the average and range of all of those measurements. So which of these methods should you use? On an exam, just use whatever the question provides you with. If they provide you with multiple trials, use the multiple trial method. If they provide you with a picture of an instrument with some graduation lines or with a digital display, use the digital instrument or analog instrument method. And if they just provide you with an absolute uncertainty, plus or minus some number, just use that. But in your own experiments, for example, in your practicals or in your internal assessments, it is good to use and compare both methods. They should produce very similar results, and if they don't, you might discuss why. There are arguments for which of these methods are better. Generally, manufacturers have more skill and knowledge than you do, especially about their own instruments that they have designed and produced, so you can trust their instrument. On the other hand, you are taking multiple trials, and your measurements likely better reflect your current environment. So there are potentially advantages and disadvantages to both of these methods. All right, we must discuss propagating uncertainties. So just like with significant figures, if we're doing math operations and calculations and using formula, the results that our calculations spit out also need to have uncertainties, just like they also need to have significant figures that follow some rules. So first, when adding or subtracting measurements, add uncertainties together. Algebraically, that means if you have some number result n that came from measurement A plus measurement B, or A minus B, then delta n, remember that's your absolute uncertainty for your calculated number. Delta n equals the absolute uncertainty of A plus the absolute uncertainty for B. This is never delta A minus delta B. All right, I should have mentioned that the triangle always means delta. It's the Greek letter. So when I say delta, I'm referring to that triangle. So it's never delta A minus delta B, it's always plus. Even if you are subtracting A minus B. Okay? Because uncertainties always add together. You always get like
more and more
total when you're adding and subtracting multiple values together. So let's go back to our pencil image here that's being measured with a ruler. We define the position of the left side of the pencil and the right side. And they were 16.5 plus or minus 0.05 and 1.00 plus or minus 0.05. So to find the actual length of this pencil, you must do a subtraction. The right side minus the left side. So you can easily find the output value, which is just 15.50. That's 16.50 minus 1.00. But the absolute uncertainty of this result is the absolute uncertainties of the inputs added together and combined. 0.05 plus 0.05 is 0.1. But you need that extra 0.10, because you've got 2 decimal places in your output, just as your inputs had. And so you need to indicate 2 decimal places to match that in the absolute uncertainty. Okay, so you could not write plus or minus 0.1 or 0.100. You've got to specifically match those 2 decimal places. Okay, so that's quite easy. Now, what about if you multiply or divide measurements? If you do that, you add relative uncertainties together to calculate the relative uncertainty of the result. And this is where most students lose me. So if you want to really understand what's going on here, you've got to listen carefully and watch carefully at what's going on. So algebraically, this means if you have some number result that came from A multiplied by B, or A divided by B, or B divided by A, all of these, if that's the case, then your delta n over n, which is the relative uncertainty in your calculated number, equals the relative uncertainty from measurement A plus the relative uncertainty from measurement B. So you cannot add the absolute uncertainties together directly. We need to move into the realm or the universe of relative uncertainties and then perhaps move back later if it's required. So I have one quite in-depth example here that I'd like to show you. Imagine that we want to find the density of this cube and its absolute uncertainty. And I have an image of this cube on the right, a length, a width, and a height of L. So we should probably know that density is a measure of mass per unit volume. We can write that as the Greek letter rho. Okay, this is not a P, this is the Greek letter rho, equals M over V, mass over volume. All right, a student measures the mass as 15.0 plus or minus 0.1 grams. They measure the side length of the cube as 12.30 plus or minus 0.10 centimeters. So right away, the first thing that you should do here is calculate that density. Forget uncertainties. Just take the pure mass measurement and the pure length of the cube side and calculate density. Okay, this is often worth like 1/3 or 1/4 of the marks on a test just to calculate this final value. So we can do that. 15 grams divided by 12.30 centimeters all cubed. That will generate an answer 8.06 times 10 to the minus 3 gram per centimeter cubed. Keep your 3 significant figures from the mass, which is the lowest. Okay, so that part is easy, but it's worth a significant proportion of marks on tests. So do that first. Now we can consider uncertainties. So what do we know? We know the mass plus or minus its absolute uncertainty, m plus or minus delta m equals 15.0 plus or minus 0.1 grams. We know the length of a side of the cube 12.30 plus or minus 0.10 centimeters. L plus or minus delta L. Now, for density, we're going to need mass over volume. So let's consider volume first. If we want volume plus or minus delta V over V, a volume plus or minus some relative uncertainty. We'd like absolute, to be honest, but because we're going to be going into the realm of relative uncertainties, this is what we need to do first. So the volume is just equal to the length times the length times the length, plus or minus, well, delta V over V, according to what I showed as a rule on the previous slide, is equal to the relative uncertainty in each of the multiplied measurements used to create V. So each of my multiplied measurements, I had one L, and another L, and another L. So I'm going to take the relative uncertainty of each of those and add them together. Delta L over L, 3 times. So this is a bit long. We can simplify this. This equals L cubed plus or minus 3 times delta L over L. Then I can put in some numbers for this. 12.30 cubed, and that will be grams per centimeter units. Oh, sorry, just centimeters. So 12.30 centimeters, all cubed, plus or minus 3 times 0.10 over 12.3, and those units will cancel out. This equals 1,861, I think rounded up from 60 point something, but 4 significant figures, plus or minus 0.02439, a unitless decimal that represents a fraction. Okay. So that is V plus or minus delta V over V. The volume calculation result plus or minus its relative uncertainty. So one way to think about this is that that's about 2.5 or 2.439%. If you would multiply that by 100%, you would get that number, about 2.4%. All right, so that's a chunk of this question finished, but not nearly ended yet. So I'm going to add that to our list of things that we know. The volume plus or minus delta V over V is 1861 centimeters cubed plus or minus 0.02439. Now I can move on to the density, which is the main target. So the relative uncertainty in the density, delta rho over rho, will equal the relative uncertainty in the mass plus the relative uncertainty in the volume. Why is that? Because in my key equation at the top, rho equals m over v, mass divided by volume. When you divide or multiply measurements, the relative uncertainty in your calculated result will equal the relative uncertainty of each component in that equation added together, as long as they are multiplied or divided. Now I can put numbers in here. I know my delta m was 0.1 and m was 15.0, and I know delta v over v from the previous slide, that was 0.02439. So this will increase my relative uncertainty up to 0.03106, which is about 3%. So my volume had uncertainty of around 2.4%. But when I go to density, I need to include the uncertainty of mass, the relative uncertainty of that. So that's going to increase my relative uncertainty in the density up to about 3%. All right. Now this question is asking us for absolute uncertainty, not for relatives. So we need to do a few more steps. I want the absolute uncertainty of density, rho. So delta rho. It must be true that delta rho over rho multiplied by rho equals delta rho, okay? just bear with me for a second. When we were doing units in dimensional analysis, we could cancel out units that were above and below some fraction, right? They would cancel out to 1. Same thing here. Delta rho over rho multiplied by rho. Rho itself will cancel out. You'll be left with delta rho. All right, so put the numbers in. Delta rho over rho from the line above is 0.03106, about 3%, multiplied by rho itself. That was the very first calculation we did on the previous slide, 15 divided by the length cubed, which was 1861 centimeters cubed. This equals 2.5 times 10 to the minus 4 gram per centimeter cubed. Okay. That is delta rho, the absolute uncertainty with units of grams per centimeter cubed. It's no longer a fraction. But you might remember on the previous slide that the density measurement, or the density result of the calculation, was times 10 to the power of minus 3. And so when we combine this together to create a final line of density plus or minus absolute uncertainty, we're going to need to change this number also into a power of 3 by moving the decimal place 1 to the left. So let's do that. Density plus or minus delta rho, the absolute uncertainty of the density, is equal to 8.06 times 10 to the minus 3 plus or minus 0.25 times 10 to the minus 3 gram per centimeter cubed. Same power of 10, same number of decimal places at 2, and units written on the far right-hand side now, gram per centimeter cubed. This is the correct way and the only way to answer this question, or to fulfill this request of you. Find the density of this cube and its absolute uncertainty. Alright, quite a few steps, very easy to make mistakes when you're writing this down or putting it into your calculator. I'd recommend you do everything at least twice to make sure you get the same result each time, make sure it makes sense, and it's displayed again with the same powers of 10 and decimal places. So you might have noticed me sort of following some rules in how I wrote those things. I'd like to just summarize them. A plus or minus A with units on the right. This is a number with its absolute uncertainty. Example 1 plus or minus 0.1 meters. When you have it written this way with absolute uncertainty, your decimals need to match. So I have 1 decimal place written in each of these. Another thing I should mention is that uncertainties generally do not have significant figures. Significant figures is a property of the measurement or the calculation result. Uncertainties just have matching decimal places to those measurements. All right, A units plus or minus delta A over A. This is the number with its relative uncertainty. So you could write 1.0 meters plus or minus 0.10. That fractional uncertainty on the right, or its relative uncertainty, has no units. And the decimals here do not need to match. And as I mentioned, uncertainties don't really have significant figures, so it's up to you to choose how many significant figures, or how many digits that you write in that relative uncertainty section. I usually write about 4, just to be safe, but I would say no more than 4, just to save yourself some time, and no less than 2, just to keep enough information inside the fractional value. Okay, A units plus or minus some percent. This is the number with its percent uncertainty. In this case, again, the decimals do not need to match. 1.0 meter plus or minus 10%. So that matches the yellow 1 plus or minus 0.10, and it matches the blue plus or minus 0.1 meter. They all represent the same thing, just different ways. Okay, one more thing. Suppose we have this equation, y equals root x, or the result of some calculation y equals the square root of some measurement x. Another way to represent that is x to the power of 1/2. That's equal to root x. So delta y over y, what is that in this case? Well, if you think about what we did for volume in my example previously, we had a length cubed, and that ended up being 3 times the relative uncertainty, would be the volume relative uncertainty. And that is actually a general rule that you can do. So if you have root x, then delta y over y equals 1/2 times delta x over x. 1/2 times the relative uncertainty in x. And then in the general case, if x is to the power of n, even if n is less than 1, like half or a third or whatever, then delta y over y is n times delta x over x. So this is not very common. Every once in a while you might come across it, but I think you should know. All right, now we need to get into uncertainties in graphs, and specifically slopes and intercepts. This will be the last section, but bear with me. Any measurements that you make that have uncertainties can also be graphed. So suppose I have a distance versus time graph here. Distance on the y-axis, time on the x. Well, maybe I make one measurement and I get one data point. It took 12.8 plus or minus, or sorry, my object traveled 12.8 plus or minus 1.2 meters in a time of 5.2 plus or minus 0.3 seconds. So I can put that data point, I'll draw it as a blue dot here right in the middle of this graph, but I'm also going to draw what are called error bars, okay? So on the graph, this is a physical representation of the range, the uncertainty range that you have. So I have, for time on the x-axis, 0.3 seconds in front and 0.3 seconds ahead represents a full horizontal error bar. Similarly, for distance, I have plus or minus 1.2 meters, so 1.2 meters above and below my blue data point, I'll have my error bars. So these bars, you can see, will trace out a kind of area. This is known as the zone of uncertainty. So I'm saying I'm confident the true value is somewhere in this zone, but it could be anywhere in the rectangular area. All right, I should also mention this graph and image was generated by Claude AI. So what if I get a bunch more data points? Maybe I'll collect 1, 2, 3, 4, 5, 6, 7 more for a total of 8 data points. For any point t, d, the time can be represented as time plus or minus delta t, the time plus or minus its absolute uncertainty. The distance can be represented by d plus or minus delta d, its absolute uncertainty. And so all of these points will have their own error bars and their own zones where I'm saying the true value falls somewhere in that zone. All right, bear with me, we're getting to where uncertainties and slopes come into play here. So, what if I want to find the slope of this? The slope should be representative of the speed of this object. I know that because I know v equals d over t. Speed equals distance over time. This is more of a physics thing than chemistry, but it's just I'm choosing it because it's a simple equation. Okay, so what you need to do if you want to find the slope of this, which should represent the speed v, and you want an uncertainty for that speed, okay? If you just draw a line of best fit through these blue points, you will get a slope, but you will have no idea what the uncertainty of that slope is. And oftentimes you need to know what the uncertainty is. So you need to draw two slopes, a maximum and a minimum. And both of these slopes, these lines, need to go through all of your zones of uncertainty. So that's what I've done here. I've drawn one that's as steep as possible. I'll call that the maximum possible slope. And I've drawn the minimum slope, the most shallow possible slope that can go through all of these zones of uncertainty. And you'll see that these lines cross each other somewhere around 4 seconds there. That point's not really important, but there needs to be a point like that, otherwise you haven't drawn the lines quite correctly, and it should be ideally somewhere near the middle of this whole graph. Okay. Now, find the slopes of both of those lines. This requires some mathematical skill and technique. I'm hoping you've learned this before, but the slope of a line is equal to y2 minus y1 over x2 minus y1, or the rise of the slope divided by the run, the horizontal distance that it covers. So we can do that. If I'm going for the maximum possible slope first, I've labeled these 2 points with yellow dots. So I'm going to take 26 minus 0 over 10 minus 0. And that comes out to 2.6 meters per second. Next, the minimum slope. I'm using these blue points. So y2 minus y1, I've got 24 minus 2. And then x2 minus x1, I've got, again, 10 minus 0, same as before. Basically the whole range of this graph. And the bigger the range that you use, generally, the better this will work. Okay? So that ends up being 2.2 meters per second. One more thing I want to mention is sometimes it's not really possible to do this, to draw these two lines and have them go through every single zone of all your data points clearly. In that case, what you should do is identify some outliers, okay? So take one point that's kind of the farthest away, that's screwing up all your efforts to make lines, and circle it and say, labeled as an outlier. And then just ignore it and treat it as a random freak of nature, a random chance that something went way off, and exclude it from your data points. Okay. Next, your slope estimation, which is also your estimation for the speed of this object, can be taken as the average of the slopes of these lines of best fit. So the average in my example will then be 2.4, because my steep slope was 2.6, my minimum shallow slope was 2.2, so the halfway point in between those is 2.4. All right. Now, the absolute uncertainty in the slope, this is the important part. It is the difference between the average slope that you calculated and the maximum or the minimum. In this case, that is plus or minus 0.2 meters per second. Again, this is also half of the range of the slopes you are considering. If you're considering the steep slope all the way down to the shallow slope, the maximum all the way down to the minimum, half of that range will be equal to your uncertainty in the slope that you report. Putting this all together, that means the slope that you report for this data set is 2.4 plus or minus 0.2 meters per second. So that's the speed plus or minus its absolute uncertainty. Next, one more thing. You will often need graphical intercepts as well, where these lines cross your x or y axis. But follow the same logic, okay? Report the intercept as the average of your two lines, your maximum and minimum lines, and your uncertainty will be half of the range of those intercepts. In my example here, the y-intercepts, or the distance axis intercept average, is 1 meter. Okay, I've got the yellow dot at 0 and the blue dot at 2 on the distance axis, so the average of that would be 1. The range, though, is 2 meters from 0 up to 2, so you can report the intercept as the average, 1, plus or minus half the range, half of 2, which is 1 meter. 1 plus or minus 1 meter. Okay. So you probably want some practice. Unfortunately, there do not seem to be as many convenient quiz websites as I had for significant figures and scientific notation. So I do recommend a worksheet that I will post in the description of this video. I can't really find the original author of that worksheet other than it was by someone named Ms. Tori. So just be aware, I didn't make this myself. I think it's a good worksheet. But Ms. Tori made it. Let's go see if we can take a look at that, actually. Quickly. Right, so here it's called Uncertainty Problems and Answers. The answers are already provided, so if you don't want to see them, you would have to hide them or something, but anyway, there's a lot of information included, including graphing as well, which is good. There might be a little bit of expansions beyond what I've taught you in this lesson, but still, give it a try. All right, let's go back to my slides. So that brings us to the end of math and science communication. We've learned it, but we can't forget it. You have to consistently use it. So before we jump into actual chemistry in the next video, some points. Chemistry is the study of energy transfer between small particles. Nature tends towards low energy states. If a system is high energy, try to think about the reason. Okay, these are just some really important points of view that I think you should have as you're studying chemistry. It's all about energy, energy transfer, and the tendency of nature to move towards lower energy systems. If you are unsure of what will happen in a given system, think about how that system could reduce its energy. That's most likely the path that it's going to take. All right, so I'm excited to get to some real chemistry in the next videos and series of things. So hopefully you've enjoyed this and learned something about experimental uncertainties. Thank you so much for listening, and I hope to see you in the next one. Best of luck. Goodbye.